Math 1314, Tyler Junior College, Section 4.3, Properties of Logarithms, Change of Base Property. This will most likely be the last video in this series. I may do a second one to demonstrate what we're going to discover a little bit more in depth. But the last topic is going to be called the change of base property. Now, up until this point, we discovered quite a few properties of logarithms. We had the original 6 that used to be here. We recently discovered the product rule, the quotient rule, and the power rule, which collectively could allow us to condense a logarithmic expression into a single logarithm, or vice versa, expand a logarithmic expression in an effort to minimize each logarithm's arguments. Just a reminder, the benefit in condensing is that we're going to use it to, I'm not sure if I've said this yet, but in the next series of videos, we're going to use it to help solve equations. The benefit of expanding a logarithmic expression is more based in calculus, where it's easier to do calculus to a logarithm whose argument is minimal as opposed to an argument that's all cluttered up. Well, we have one more obstacle to overcome, and the change of base property will help us overcome that. Here's the scenario. Your calculator has a log button, L-O-G, and recall that that's base 10, and an ln button, and recall that natural log is log base e. But you need to approximate log base 3 of 14. How? Now, some calculators are sophisticated enough these days where you can type in a logarithm and enter the base that you want. But several calculators, including one that I don't have, actually I do, it's right here. Some calculators, like this TI-30XA, has a log button and an ln button, but doesn't allow me to enter a logarithm of the base of my choice. But can we still get the answer to log base 3 of 14 using only the buttons log or possibly ln or some combination of them? The answer, of course, is yes, but the better question is how? I'm going to take you through the journey between the beginning and the end, and from that we're going to formulate a general plan of attack, and it'll be called the change of base property. One strategy in math for figuring out what something equals is to just call it something generic like x. So we're going to let x equal log base 3 of 14. Now normally when we're solving we want to get the x by itself, and this one already is. But in this strategy you call it something like x, and then you manipulate the equation, move things around, do legal moves in an effort to restructure what x is equal to. Here's what I mean. If I said do something with this logarithmic equation, there's not much we could do at this point except rewrite it in exponential form. So what would this equation be in exponential form? The easiest way to convert a logarithmic equation to exponential form is to remember that the answer to a logarithm is a power that turns the base into the argument. I know I say that a lot. The answer to this logarithm is being called x, so it's the power that's supposed to turn the base into the argument. In other words, x is the power that is supposed to turn 3 into 14. So there's the exponential form of this logarithmic equation. 3 to the x power equals 14. I know I'm trying to figure out what x equals, and I just buried it up in the exponent. That seems a little bit contradictory to, or not contradictory, counterproductive to what I'm trying to accomplish. What does x equal? But let's start from here and see if we can figure out a plan of attack for getting the x by itself. You're probably saying just put it back in logarithmic form. I'd be right back where I started. Let's do a different plan. Notice that the x is currently located in the exponent. I kind of want to drag it down. I'd like to be able to pull it out of the exponent and put it on the ground level with everybody else. But we can't just arbitrarily grab a power and put it in front. Oh wait, there was a time when we could. What was the rule that allowed us to take a power and move it in front of something? Oh, the power rule. Recall that the power rule said if we have a logarithm, any base, any argument, we'll call it capital M, raised to a power, we'll say to the nth power. Then the power rule says that we can take that power and put it in front and leave the rest of the argument inside the logarithm. Well, this is exactly what I want to do right now. I want to grab a power and drag it down. The only problem is I can't use the power rule because the power rule says that works if this is inside of a logarithm. Okay, let's put it inside of a logarithm by taking the logarithm of both sides. But now we have a choice to make. If I take the logarithm of both sides, I have to choose a base to use on that logarithm. What base should we use? Well, not base 3, it'll take us back here. Oh, wait a minute. If we're trying to use a calculator, we should use a base that most scientific calculators can handle. Base 10 or base E. Either one will work. Let's use base 10. So we're going to take the log of both sides. Giving us log of 3 to the x power equals log of 14. And remember, the motivation for that was to set up the power rule, which will allow us to bring the power down. Because right now it's in the exponent. So let's use the power rule. Use the power rule on the left. Bring down the power and put it in front. Now we have x times log of 3 equals log of 14. Now remember, I'm trying to figure out what x equals, or at least something besides what it started out to be. Well, I'm one move away from getting the x by itself. The only reason it's not by itself is because it's multiplied by log of 3. Now what's log of 3? Well, at this point I really don't care because I'm focusing on getting the x by itself. The only thing I know about log of 3 at this point is it's a number. And I know how to get rid of numbers that are multiplied, so do you. Divide both sides by the number that you don't want there. We're going to divide both sides by log of 3. Divide both sides by log 3. And if we do that, it will isolate the x, and it will put a log 3 underneath the log 14. So look where we are now. We're back to x equals, but now we're to x equals something that looks different than the way it started, and this can go into a calculator, excuse me. We've essentially changed this from base 3 to a new base. We chose base 10. And this is something I could put in a calculator. Using a calculator, now how you put this in your calculator depends upon if it's a one-line calculator or a display calculator. Display calculator displays the whole problem before it gives you an answer. You pretty much type exactly what you see. But for a one-line calculator is, let me see if I can zoom in real close here. Hold on. Let's try this. There we go. A one-line calculator will only display the last number you entered or the last answer it calculated. For a one-line calculator, to evaluate a logarithm, you have to enter the argument first and then press log. So, to evaluate log 14 divided by log 3, here's how we would do it. Let's focus that. We would have to first press 14, because that's the number we wanted to take the log of. So 14 log, there's the answer to 14 log, divided by, now I need to divide it by the log of 3. So again, I have to press the 3 first, and then the log button. What you're seeing right now is the answer to log 3, not the answer to the division problem. To finish it, I have to press equals, and that should be it. to 4 decimal places, 2.4022. 2.4022. Now, if you have a calculator that will allow you to type in log base 3 or 14, you should get the same answer to 4 decimal places. How do we know that's the correct answer? Well, because we know what the answer to this log is supposed to do. It's supposed to be the power that turns 3 into 14. So we could check it by taking 3 and raising it to this power. It will not give you exactly 14 because we rounded off the answer. In fact, the answer to this logarithm is an irrational number. The decimal will go forever and never repeat. But if we did, I'll put the calculator back up on the monitor or on the screen. Okay, let's focus. Come on, focus. There we go. All right, if we do 3 to the 2.4022 power, I believe I rounded my answer up, which means this answer is actually a little too large, which means this should come out a little more than 14. It did, but it's pretty darn close. So our plan of attack to evaluate the logarithm by calling it x and then doing some algebraic gymnastics, if you will, to rewrite what x equals and make it calculator workable, seemed to get the job done. This was about 14. But can we make this a little bit more general? In other words, do we have to do this every single time? Absolutely not. Math is about a lot of things. One of the things it's about is making observations and trying to draw generalizations from them. What observations are we looking for? Well, look where we started and look where we ended. I think it's almost transparent what happened. This logarithm became a ratio of logarithms. And by the way, I forgot to mention this earlier, don't cancel these logs. You can only cancel parts of multiplication problems. There are no multiplication problems up here. Remember, log is a function. It's not a multiplication problem. I think it's pretty transparent what happened to the pieces of the original logarithm when it became the ratio of 2 logarithms. The original argument became the argument of the log in the numerator, whereas the original base became the argument of the log in the denominator. There's actually one more number that snuck into this because we had to make a choice here. Remember when I said let's take the log of both sides, let's choose a base? I happen to choose 10. I could have chosen any base I want. I could have put log base 2, log base 7, log base 1,000,000 if I wanted to. What would happen to those bases if I chose a different base? Well, the power rule would still happen. We would still divide. We would get this answer, except both logs would have that base. So we really can change the base to anything that we want. Let's see if we can generalize this. Change of base property. The change of base property is real simple. It says if you have any logarithm, any base, so we'll call it base B, any argument, we'll call the argument A, that's a good letter for argument. You can rewrite it as the ratio of 2 logarithms. The original argument is the argument of the log in the numerator. That's exactly what we said over there. The original base is the argument of the log in the denominator. But in this process, when we took the log of both sides, we can choose any permissible base that we want. So to represent a new base, because right now it's saying base 10, but it can be base anything, I'm going to put a new base of C and stipulate that this is true for any C that is an allowable base, which is any number greater than 0, but not equal to 1. Remember, those are the criteria for the base of a logarithm, also for the base of an exponential function. I know we kind of went long in this video, but I'm thinking about stretching it a couple more minutes so we don't have to have one more video. You know what, we'll cut this one off. If you're good with the topic, great, but I'm gonna make one more video just illustrating another example in a calculator and how you can actually use the change of base property to totally not have to worry about a calculator in certain circumstances.